And one of the things about this example is that even though it's so much longer, that actually makes it better for practicing with synthetic division because it gives you more opportunities to go through that step that you have to repeat and repeat and repeat, and it gets into your head a little bit better. Okay, so let's begin. The first thing you do is you write that upside down division sign, yeah? And it's going to be a pretty long one because we've got a lot of numbers to fit, right? Okay, now there's a number that goes up here. What is it? In this case, it's 2, right? The way you'd say it is, where does it actually come from? It's the solution to, if we'd made this an equation, right? X minus 2 equals 0, right? Alternatively, by the way, just as a bit of notation that I sort of left off from Wednesday, but you can say that this, right? This is a polynomial equation, right? You can say it has solutions, one solution, or you can say it has roots, right? Because it's an equation, you could graph it, right? However, if I went from an equation to an expression, does anyone know what the difference between an equation and an expression is? Yeah, so an equation has an equals sign, right? But an expression, it's just the x minus 2 on its own. It's not equal to anything, okay? Now, since it's not equal to anything, you can't solve it. Does that make sense? And in the same way, because it's not equal to anything, you can't draw it, right? So it can't have roots, right? However, this number, 2, right, is just as important to this expression as it is to this equation, okay? So it's still meaningful. We can't call it a solution or a root. So you may remember this from year 9. It's called a 0, right? Because if you put 2 into there, it makes that polynomial equal to 0, right? And sometimes there are multiple ones. All right, so 2. We've written down the 0. Now let's follow on and write down all our coefficients. Okay, so we go 2 minus 4. 0. Watch out. Read carefully. Okay. Minus 5, 2, 3, minus 1. Okay. Remember, these correspond to how many x to the 6s, how many x to the 5s, how many x to the 4s. Answer, there are none, right? Please include that. And so on. All right. Now what do I do next? Let's draw another line underneath. And my first step in my actual working out of the, and by the way, if you haven't gone and looked it up, it is the quotient that you end up with, okay? What do I do? Okay. I just take the leading coefficient. You just jot it down, yeah? Okay, now what do I do with that? Multiply, and here's where it starts to cycle, yeah? Multiply, add. Yep, okay. Multiply, add. So far so good? Multiply, add. Multiply, add. Yes? So far so good? Multiply, add, multiply, add. Okay, any problems with the arithmetic? Does it check out? I think it looks okay. All right, now that I've got my coefficients, right, I want to map that to the fact that this was degree 6, right? Degree 6, and I was dividing by degree 1, okay? So therefore my quotient should be degree 5. Okay, likewise, if I was dividing degree 6 by degree 3, what I'd end up with is degree 3, right? And so on. Okay, so therefore this has an x to the 5 attached to it. That's the x to the 4. That's the x to the 3. This is going to be an x squared, right? Minus 8x. There's the constant, and there's the remainder. Okay? All right, now let's write this as the division transformation, right? I'm going to take this guy, right, and I'm just going to do, I'm going to call him P for polynomial. Okay. I can say, therefore, that this polynomial is equal to the divisor by the quotient, 5. Okay, divisor, quotient, and then you add your remainder on the end, which just corrects and make it all make sense. Okay.